Okay, well, thank you for coming back after lunch. Our last session of the day will be led off by Scott McIntosh, who will talk about 140 years of the extended solar cycle. Take it away.
Subtitle is Stuff. Congratulations, everyone. It's Friday afternoon. Well, I've been beavering around, going to meetings left, right, and center. I've been here for about 3 talks, so I apologize. I don't. Do you want me to put one on, Yuri? So you can hear my awesome accent a little bit clearer? Speak your English. No speak of the English. All right. So this is work that we've been doing basically for the last 7 years around this concept of the extended solar cycle. And for those of you that don't know what that is, you're about to find out. And for those of you that do know what this is, you can leave the room whenever you want. But the basic premise is that the sunspot butterfly diagram is only a subset of the larger scale evolution. And what we've been tracking is that larger scale evolution. And furthermore, that large scale evolution, the thing that ends up being the 22-year magnetic activity cycle, is extremely periodic and repeats, almost like clockwork. So I don't know what the big problem is. But anyway, we'll get there. I'm being rather flippant because it's Friday afternoon and beer is calling me from somewhere. And so, you know, I have a concern. This is, I put my kind of lab director hat on and this thing's not focused and my eyes are screwed up. Whether or not we still ask the big questions. Do we still ask the right questions? Do we encourage students and postdocs to ask the right questions? I always tell the undergraduates that I'm working with, or whoever else is, they have to question everything, particularly the stuff that comes out my mouth. But you have to question absolutely everything. It's the only way you're going to learn. And of course, this is a rather provocative and old cartoon that many people may have used, but it's the old one where someone's looking for their keys and looking for their keys under a certain lamppost. But it just turns out that that's where the lamppost happens to be, where they're looking for their keys and not the one that they should be looking under or where they should be looking. So we are looking at these observational clues that maybe hint at we should be looking somewhere else. At the sun, though. So the whole premise boils around the work that I started as a postdoc a long time ago around these little guys. These are called EUV breakpoints or coronal breakpoints. And for the longest time, I thought they were just associated with supergranulation. You know, you get opposite polarity magnetic flux elements come close together at a supergranular vortex, and boom, you get a little tiny active region. That doesn't work. Why does it not work? Well, it's because the corona is not pockmarked with them. Sure, there's lots of them. There's 382 of them on this image, but they're not everywhere. They have an apparent length scale. If you do a skeleton, a segmentation from dot to dot here, the average length scale is about 100 megameters, right? They are not every 25 megameters. It's about 100, 150. And what's more, after you've cataloged these things in one image, we've got 22 years of data. We can catalog them till the end of time. And so if you plot the EUV breakpoint density here as a function of time, and this is largely from SOHO EIT, you see some kind of crude features. Can someone turn the lights down, if possible? But one of the things you'll instantly notice is that these chevron-like bands of EUV breakpoint density overlap one another. So even though cycle 24 is kicked off and starting here, it extends back visibly traceable to about 2007. And if you're really cunning and dirty and average a lot, you can see it back to 2005. Okay? Also, the same happens back in 1997 between cycle 23 and 24. 22 and 23. So there's these overlapping systems present. So it's not just a simple kind of binary on-off switch, right? or maybe it is. If you add into this mix a length scale that appears in the photosphere, right? These EUV breakpoints, back in 2010 we published a paper that associated these EUV breakpoints with a particular length scale that appeared in the photospheric magnetic field, again of the order of about 100 megameters. If you added that to the breakpoints, you get a picture that looks like this now. Green, 22, red, 23, purple, or blue here, 24, and purple. What's the purple? It's 25. Even this plot, which ends in 2013, we could see cycle 25 at high latitudes in the northern hemisphere in 2012. Go into why. For those of you helioseismologists in the room, that pattern pretty much matches the torsional oscillation. No big shock, because someone actually published this back in 1988. I found that out when I was 95% of the way through writing a paper on it. As always happens, right? Someone else did it first. But what they didn't do was understand the phasing. And they noticed what we noticed, and if I go back, you'll be able to see it a bit more clearly, that there's epochs, there are particular events, there are landmark events in this data set. For example, where this white dashed line is. All of a sudden, it goes from having activity at the equator to nothing. Is it? It's probably better if it's muted, to be honest. There we go. Oh, Jesus. All right, I really do apologize now. So, I'll move it down a bit. There we go. So these events, it turns out, are pretty important. So remember them. We'll get into a little bit more information about them later, but we called them terminators because we couldn't think of a better name for them. But basically what happens is activity drops at the equator, but it picks up rapidly at mid-latitudes. Kind of looks like the bands that are near the equator die, and that flips a switch somehow. So anyway, looks like the torsional oscillation, a lot like it. But what we noticed was, we have these termination events. But what we also got was, where the bands start to migrate, where these features start to migrate at high latitudes, was coincident with the hemispheric maxima in each hemisphere. So you could see a band moving from 55 degrees down towards the equator in the northern hemisphere that started in the middle of 2000. Whereas the one for the southern hemisphere only started in late 2002. So there was a 2-year phase lag between the two of them. Funnily enough, that corresponded between the hemispheric sunspot maxima as well. Are they related? Of course you'll know that these systems all have opposite magnetic polarities, right? So if this is a positive polarity branch, this is a negative polarity branch. So at some point, the fact that there's these opposite polarity systems in this hemisphere is dialing down the productivity of sunspots in that hemisphere. But then what happens when you extinguish them? Anyway, so this, I apologize for, is a schematic. There's very little information in here other than the band start times at high latitudes and the polarity flips. And right now, for this part of the talk, the stuff that's going on at high latitudes is almost complete fiction derived from Roger Ulrich's 2010 paper. So it roughly describes the evolution at high latitudes. But what these basically are the bands of the 22-year magnetic activity cycle. It takes 19 years for this guy to meet its end, 19 for this guy, etc., etc. In a broader context, once you derive what these measures look like, and you can go in and look at sunspot number distributions as a function of time, we can start to bootstrap our way back in time and say, okay, when the sunspot area in each hemisphere goes above 100 millionths for the first time, we've gone through a transition. Something's just kick-started the branches of the butterfly diagram. From the detailed observations, we could do that back 22 years or back to 1995. But we've taken this analog and gone back further, right? So we just used the butterfly diagram and the sunspot areas that are cataloged back to 1860 to define basically the landmarks that make this schematic. So hemispheric sunspot number maximum marks where the band starts in each hemisphere, and it dies identically when the next band's wings start. Sounds a bit crude. Well, it is a little bit crude, except for the fact that the thing's like bloody clockwork in both hemispheres. If I go back and look at the timing between consecutive maxima of the same polarity, it's 21.85 years plus or minus 0.3 in the north, and it's like 21.7 plus or minus 0.4 in the south. Something's repeating. But it's not at mid-latitudes, it's at high latitudes. Cunning. Anyway, so let's go to the kind of historical or the hysterical part of this. Since 1880, our Italian and French colleagues have been determining the positions of filaments on the solar disk. Those filaments on the solar disk track where there's neutral lines in the global magnetic field, right? And actually, this is taken from a paper in 1933 that they assessed the hemispheric distribution of filaments in the northern and southern hemispheres and noted that there are preferential zones. There were places where there was peaks in the distribution. And furthermore, they tracked them in 1933. And so here's the annual density function of filaments on the solar disk. The thing you'll note very prominently are these things called subsequently called the rush to the poles, these poleward surges. But you see effectively the butterfly wings, and you also see the fact that it looks like even the filaments are bounded by 55 degrees. If I take where the local maxima are of this plot, and you won't be able to see these dots, but there's a skeleton of where all the local maxima are, it'll look a little bit better in the next version. So the Moudon data set is rotation by rotation, whereas the Archetri data set was published in 33 as annual variability. And so here's now your filament distribution on a rotation by rotation basis, and there's all your maxima plotted. Can anyone start to see the pattern? Now, this is unfortunately, at this time, I hadn't quite got hold of the Russian data that takes us up to the present day. So I had to go looking for something else. And in 1939, when Leo built his first coronagraph, he started to study the evolution of the green line. And of course, like filaments, the green line tracks the global shape and morphology of the corona. And so what they decided to do was on a day-by-day basis, they would take scans around the corona, marking out where all what were primarily the helmet streamers were. So these extended structures, so you'd have a maxima here, one there, one there. And they did it day in, day out. And the green line record goes from 1939 right up to the present. And it looks a lot like the filament record. Shock horror, because they're basically effectively measuring the same stuff. You get the rush to the poles, you get the butterflies. And when I go in and look at this daily data and map out where all the maxima are as a function of latitude, I get this plot. So now you're asking, what's Crazy Man going to do next? Well, I take my existing 22 years of data and do exactly the same analysis. And I get this. What happens when you put them together? Let's look. You get 140 years of the sun basically doing the same thing over and over and over again. How do you test that? Let's see. Well, I don't need to show this. I think I can skip through this. It's basically showing the contemporary data. Pattern repeats. So the corona is reflecting what's been measured down in the lower part of the atmosphere, which is measuring the filament evolution. and all kinds of things. But there's a trick you can do. You can use an old meteorological technique called actually it was developed for studying solar cycles, but it's been widely used in meteorology and climatology to look at trends, superposed epoch analysis. And so if I break my data down, if I assume there's a prevalent time in my data set that repeats, that recurs, and I realign all my data statistically on those recurrences, what pattern do I get? And so the first go-round for this was to use the hemispheric maxima, since I thought that that was relevant. And it's not too bad. So when I break down by maxima in each hemisphere, there's a lot of lines and grid marks for north and south here. If I then collapse all the data onto those two matrices, so it's hemispheric maxima plus or minus 11 years, I get plots that look like this. Can you distinguish between the two? All the phase lags are gone now. Part of this process removes the phase lag. There's the north, there's the south. You saw a little shift. But other than that, they're fairly identical. Now there's a trick you can do. And since we've been looking at these data, we've realized that this time frame, this important event that happens when the bands die at the equator, may actually be the most important fiducial time. But it doesn't always vary. It's not an 11-year thing. It can be 8 years, it can be 9 years, it can be 10 years. But if I take my data and use that as my fiducial time, I get a pattern for all solar cycles and for the chronal green line data that looks like this. This is the standard deviation and the skewness and kurtosis. So you can see that statistically, the pattern's pretty robust. If I use the same thing for my lovely Archatri data, it looks like a disco ball. And so this is the 51 years of Archatri data all collapsed onto one time frame using these terminator points as the fiducial. This is the Mudon data set with exactly the same fiducial. That's the chronal green line data with the same fiducial, all different epochs, same fiducial time. And there's the sunspot number all collapsed. So this is 12 sunspot cycles all collapsed onto the same fiducial time. What happens when you put them all together? That. All of those data sets collapse. Does that mean then that this is the basic unit of solar activity? It's 22 years long. You can see that it starts at high latitudes, about 55 degrees, sits there for a little while, then migrates down. At the same time that it sits there, it's also merging flux towards the poles. And then just mysteriously, it just switches off. When it switches off, it starts off again. It's pretty cool and weird at the same time. So one of the things we've latched onto here, so now I'm also including the Russian data that brings the filament record up to date, is this rush to the poles concept, this thing that the start of the polar reversal of the sun, the thing that's seen as the signature event of any kind of flux transport dynamo model. If you just plot the evolution of the highest latitude filaments in the system, this is the plot you get. 4 different observatories running for 140 years. Looks like a heartbeat, looks like an EKG. Again, if you do your superposed epoch analysis in that, you get something that looks like this. But basically, they fold. But they're folding relative to this termination event. And that's somehow mysterious and significant. So if I put my butterfly diagram on exactly the same plot now, what you'll see is what looks like is happening. And again, excuse me for being an observer, not a theorist. But when the bands at the equator die, not only do we get something triggered at mid-latitudes which switches on the production of sunspots, it also appears to trigger the rush to the poles at 55 degrees. What's even more scary is it does it over a very, very short time scale. We're looking into that time scale right now, but the premise is that that time scale is something less than a solar rotation. So you've got information. Who knows what information it is? Is it buoyancy information? Is it the pressure distributions changing? Somehow the death of the bands at the equator is being communicated globally throughout the system. Now, the weird thing about this is it's also very longitudinally sensitive. But I haven't got into that. So, you've got synchronization. I think if you talk to people about the rush to the poles, we know that the hemispheric sunspot number is not synchronized across the equator. Why the hell is the rush to the poles synchronized? Unless it's connected to something. What is it? It's always, I think, just been seen as fluff. Not really intrinsically tied. And of course, if you had torsional oscillation information going back for 140 years, it would probably look just like this. So, while the hemispheric maxima are not synchronized, the butterfly wing launches are, and the rush to the poles are. So now you start to ask yourself a question. How does this system talk? You know, in our atmosphere, and probably those of other planets, the global scale convective or circulation patterns talk to one another. They know about one another. Is that done via gravity waves? How's that done? How's it done in the sun's interior? Because for some reason they seem to know about the presence of other magnetic systems nearby. Are they directly connected? Are they indirectly connected? I don't know. So you get mid-latitude growth and the rush to the poles linked to termination. That termination point seems to be the trigger by which you can co-align all your data sets. One of the things I haven't shown, because I didn't realize it quite enough time, was that when you go through this transition, when the bands at the equator terminate, almost all longitudes light up, almost instantaneously. Right? You get activity being spawned, you get flux emergence being spawned at all longitudes after this termination event. We don't know what the moderator is, what's carrying the information. Sunspots are just part and parcel of this evolution, as are filaments, as is the global scale coronal magnetic field. The thing in red here, 55 degrees, seems to be a very critical latitude. It's the start, not at mid-latitudes. What the hell is it? Right? We all see all these other planetary bodies. You look at Juno observations of Jupiter. There's weird things going on at Jupiter's poles. There's weird things going on at Saturn's poles. Uranus, the lot. Maybe all slightly different latitudes, but there's weird latitudes. And for the sun, 55 degrees seems to be where the root of all evil happens to be, where it starts, not at 35 degrees. Is it predictable? I'll show you that in a minute, maybe. Resolved observations are required, but of course, and then I think if you can actually make sense out of this, chances are this is how you can maybe understand the activities of other stars, once you can tie this evolution to the calcium pattern of the sun as a star, and then transfer it out. Because if the sun, the boring sun, is making a very weak pattern out of a very complex interacting system, what happens when you drive the sun 5 times faster? How many bands per hemisphere do you get, and what does the chaotic interaction look like after that? So, to close, in 2013, we made these projections. Thank you. In these projections, this is basically, you can focus on this one if you want, the EUV bright point distribution. We noticed that there was an average behavior. We projected out what the average behavior was. We had also noticed that every 21.8 years in each hemisphere, there was a new band of the opposite sign being inserted into that hemisphere. And so we speculated where cycle 25 was going to appear and what rate it was going to move at, right? Guess what? Bloody well did it. Not that anybody cares, mind you, but it did it. So what's the next thing that's going to happen? Next thing that's going to happen, well, we're already kind of in solar minimum if I updated this another year, but we're within 2 years of the next termination event. Actually, we're within a year probably, which means that the bands near the equator are going to die, and instead of the odd m=1 sunspot that we're seeing right now, all of a sudden, we're going to see 5 or 6 of them pop up at all longitudes after that termination event. So cycle 25 will kick off, roughly, in early 2020, which will make this cycle a short one. So, I get this. It's up to you whether you want to guess as to whether or not cycle 25 is going to be lower than 24, but we all know that 24 was lower than 23. We expect spots late, significant spots late in 2019, and a termination event in 2020. And of course, those termination events, because it's a significant change in the underlying magnetism, have a whole host of other signatures that we're just kind of dialing into. I'm not even talking about Grand Minima. Should take that slide out. But this is the third cycle in a row it's been going down by 25%. So there it is, almost to date. Cycle 25 in full effect. We still have a 2-year phase lag between the north and the south, and everything appears to be tracking pretty well. You know, there's a lot to do. You know, these observations illustrate that the extended solar cycle is the progression of the 22-year magnetic activity cycle. I don't think there's another way to explain it. Maybe there is. You know, I think, from my perspective, one of the things I'm pushing for are continuous polar observations of the sun. Because I want to see these systems form and develop. I want to understand why at 55 degrees everything changes. The convection changes, the bright point density patterns change, the supergranules change, everything changes. Why? Why do filaments, if there's a continuous flow from equator to pole, why does a filament form at some arbitrary latitude and stay there for 10 years? Good challenge. So is it a wave-like solution to the dynamo problem? I don't know. Just a poor observer. Is the dynamo action itself, is the field primarily forming at 55 degrees? And why? The sun appears to be telling us that that's the lamppost we should be looking at. What's helioseismology seeing at 55 degrees? Is it a real challenge from the sun-earth line to see 55 degrees? Or is there stuff that we're just not interpreting properly? You know, I don't know. There's a lot of questions here. But I always come back to 55 degrees will haunt me in my nightmares, I think, forever. And I don't have any further stuff to show, so if you've got any questions, I'll take them. I can't have explained it that well. It's Friday afternoon.
So Scott, what are the keys that we've been looking for underneath the light post? Where should we be looking at? What should we be looking at?
I think we should be looking for shear flows up at those high latitudes. There's something going on at 55 degrees or thereabouts that's recurrent, Yuri. And if that's where the field form, that seems to be, there is coherent flux emergence that stems from that point. To me, as a poor observer, that's where I would train my view. Correct. So does that mean that there's something between the polar cell and that cylinder that's going on? That would be my hunch. That maybe you've got an interface going on in there that's, you've either got a toroidal system and a poloidal system that meet one another. I don't know. I think without polar observations, you won't really be able to tell. But I think that would be my hunch. But then the challenge is, can we model it? Can we model it now? What's holding back the models from seeing something weird at those latitudes?
Any additional questions? All right, thanks, Scott, again.
Just a small question. What about the long-term variation of this 55 degrees? It stays the same or?
So the RMS. Hey, Ben. Yeah. No, you're good. So the RMS, Tamuri, if I just take this plot, for example, it looks like a lot of scatter. But if I plot you the mean and the scatter's a couple of degrees. But it's 55 plus or minus 1.5 sigma over 140 years. Minus the excursions towards the poles, right? It's pretty tight. So, I don't know. That's come up with an idea. I think once you figure out what's going on there, then you're a short step away from solving the puzzle. Thank you.
How do we get a polar mission? All right.
Do you want this over your mic?
I don't want it, but I probably should have it.
So our next speaker is Ben Braun from UC Colorado. Colorado. We'll be talking about overshooting low Mach number rotating stellar convection.
Okay, let's see. Let's put the mic down low because I have a loud and booming voice, even when I'm using my inside voice. I want to talk to you a little bit about overshooting and rotating low Mach number stellar convection. I had hoped to talk to you about the interactions of both at the same time, and we're not there yet. So this is some of the overshooting work that we'll get to in a bit, but I want to show you some sort of broad advances we've been making in the modeling of low Mach number convection over the last couple of years amongst a large team. Daniel Leconet, who was here at the meeting a little earlier, Evan Anders and Jet Bordwell, two grad students here at University of Colorado. Evan's been here at the meeting. And Jeff Oishi, Keaton Burns, and Jeff Vassell. So without further ado, let's step into this. So before I start, I want to motivate things a little bit by talking very briefly about the interior of the sun and some problems in fundamental convection that have come up in the interior of the sun over the last couple years. So here's our view of the interior of the sun. So here's our cartoon view of the interior. Here's our helioseismic view of the differential rotation of the interior. What we know about the interior of the sun is it's a highly stratified region. There's a helicopter coming, that's right. Anyone have any idea of how we make the helicopter go away? Let's kill. Let me. Help. Oh. There you go. Yeah. Someone wrote to me asking me why the FBI had shut down Sac Peak. And I was like, why are you writing to me? I have no idea, but I will ask people at HAO. So there you go. Anyway, so the solar convection zone, right, spans the outer 30% of the sun by radius. It spans about 14 density scale heights of stratification between the HAO1 photosphere and the base of the solar convection zone. If you try and calculate fluid parameters for this thing, it has Reynolds numbers that are huge. It has an Ekman number of 10 to the minus 15, about the same as the Earth's core, which is kind of interesting. The big difference in some senses between the interior of the Earth and the interior of the sun is the Earth is an Ekman of 10 to the minus 15, the sun's an Ekman of 10 to the minus 15, but the Rossby number of the sun is maybe something like order 1 rather than 10 to the minus giant, 10 to the minus 6 or so. Though we've actually had a lot of question about this Rossby number in particular, and I'll come back to that in just a moment. And we have this tachocline at the base of this thing, this speed matching layer between the stably stratified interior and the unstably stratified convection zone. The convection zone has this big differential rotation. Red means it's going prograde. Blue at the North Pole means it's going retrograde. The contours are kind of constant with depth in the convection zone. Then you hit the radiative interior, and everything comes on to solid body rotation. We have no idea why, and we've often thought that that boundary layer between the two was a crucial part of the overall dynamo properties. And there have been some real open dynamo questions that have come up over especially the last 5 years. And one of them, as Nick Featherstone talked to us earlier in this meeting, is just how rotationally constrained are those motions in the solar convection zone? Is the Rossby number of the solar convection zone 1, with an overturn time of like a month or less, being the rotation period of the sun, or is it a tiny number, like 10 to the minus 2, with motions that are much lower in amplitude? And these questions have been really fueled by what some people have called a convective conundrum. We have some new measurements in the last decade from helioseismology of the convective flows in the convection zone of the sun. Those are shown here. The spherical harmonic degree is at the bottom. The amplitude runs up this way. And these red lines are one set of observational measurements with helioseismology. And these orange lines are another set of measurements with helioseismology. And the orange lines are an upper limit. So there's a huge observational tension. And both of those sets of lines are below, either a bit below for the red line or hugely below for the orange line, the predictions of simulations, 2 of which are up in the purple and the green there. So simulations are churning along at relatively high amplitude. Observations are telling us that the amplitudes are either lower or much, much, much lower than what simulations are achieving. So the sun is in a different dynamical regime than where many of our simulations were, maybe. And this, I think, is an extremely pressing question in heliophysics and the solar dynamo, and there's been kind of a scattering of work over this over the last several years, starting with Shravan Hanasoje's initial detections in 2012, and then some later work by Ben Greer in 2015, 16, and 16, and some modeling work by Jesse Lord. Okay, so as a fluid dynamicist and theorist, where this gets interesting for me is trying to understand the fundamental properties of low Mach number convection, and can we get an idea of why the models are getting different amplitudes than the observations are suggesting to us. So let's talk a little bit about what it means to try and model convection at low Mach numbers. So the reason that low Mach numbers are challenging is that sound is very fast. And if you're at low Mach numbers, then you're mostly following sound waves with your numerical technique. That's an easy way to create a lot of heat energy in your computers. It's a very slow way to actually get to an answer if you're at solar Mach numbers. So often in trying to study systems that are at low Mach number, we adopt one of a number of approximations to the actual, the helicopter's back again. We adopt one of a number of approximations to the flows. We try and filter our flows. We change the equations we're solving to try and study these low Mach number dynamics. So a small hierarchy of these. There's Boussinesq, which many of you know about. Here you say the flow's incompressible, but we have buoyancy. Our next step in complexity towards trying to model something like the sun is to adopt something like the anelastic approximation, where in some senses we're saying there's a large-scale stratification that can slowly compress or expand flows, and there's still thermodynamics, but the thermodynamics are small. If you try and generalize that again, this takes you to an equation set that shows up sometimes in atmospheric sciences called the pseudo-incompressible equations. Those, in some sense, say there's stratification, and some of our thermodynamic perturbations are big, but we're still in some kind of continuous pressure balance all the time. And you can derive this hierarchy out of Lagrangian mechanics, and Jeff Vassell and I and Daniel Lecone and some others did some work on this a few years ago trying to understand this. We really wanted to go and study some of these more advanced equations in our minds, the pseudo-incompressible equations, but we didn't have a tool for doing that. And it turns out that converting an anelastic code into a pseudo-incompressible code was a very, very hard piece of work. So out of that, we ended up kind of unintentionally creating a community tool, which I'm going to tell you about for the next couple minutes, because this was our way to try and study new physics. This is a tool called Daedalus, a pseudospectral framework. And our fundamental problem is we wanted to solve a new partial differential equation that we didn't have the tools for. So we built a tool for solving generalized partial differential equations. And it's open source, and it's available to you. So if you have interesting partial differential equations to solve, it may be something to play with. This was written by a small team of us. It was especially written by this gentleman who Daniel mentioned in his talk, Keaton Burns, who was a grad student at MIT. He's now a postdoc at the Simon Center for Computational Astrophysics in New York. And Keaton was a major part of this, but a huge amount of the success of this was the very interdisciplinary team. We've got 2 guys who break things. Those are the ones on either end up there, Daniel and myself. We've got Keaton, who writes code. We've got Jeff Assel, who actually knows math. And we have Jeff Oishi, who's done foundational things for us actually having a functioning community. So I'm going to tell you about this tool very briefly. The idea of the tool was to decouple the equations being solved from the approach being used. So it's almost like a programming language for the math you want to solve. This is what you see as a user. And the equations are put in text strings that follow a grammar. And then behind what you see, there's machinery for actually representing the time derivatives, the partial derivatives, and for calculating all the various terms, so that we spend our time playing with, well, what if we express the momentum, what if we express the nonlinear advection operator as like omega cross u rather than u dot grad u? Does that lead to better computational behavior? Turns out yes, by a substantial margin. And we can sort of iterate on those discoveries quickly. So can you. The overall structure is that the user writes a thing up in the green box, which are the equation set that you want to study and things about your initial conditions, say Rayleigh-Benard convection. You then tap into a structure that can solve your PD in different ways. So you can do time stepping with initial value problems. You can do stability analysis with eigenvalue problems. You can solve linear and nonlinear boundary value problems to get equilibrated structures or do other things like that. All of those tap into a grammar and parser and an underlying spectral polynomial representation and the appropriate solvers. Those are all written in Python, but then they sit on very, very fast libraries. So they sit on HDF5 to do file output. They sit on FFTW, and they sit on SuperLU and UmpPack for the linear algebra. The effective cost of using Python is around 5%. So we are within 5% of competitive of many of the other codes that we have tested on that are pure Fortran codes. And that's pretty cheap, frankly, for something that you can pivot around and do different problems on. The kind of interesting modern advances, so that's been around for a couple of years now. Just this year, the kind of big advance has been going from Cartesian geometries, which are easy, into round geometries. So in particular, cylinders and spheres that can capture all the way down to r equals 0 and the singularity that's there. And we have a couple of papers that are up on arXiv and are in the middle of the referee revisions right now, one led by Jeff Assel that does the math, one led by Daniel that does benchmarking problems and tests these against known problems of convection and MHD dynamo work. And the sort of core idea of these was we found that, so tensor calculus is hard, but there are some simplified basis sets which make the tensor calculus automatable so that we don't have to spend all of our time trying to solve a particular set of tensors. So it turns out if you go to spin-weighted spherical harmonics, and if you use some clever Jacobi polynomials radially, then you can come up with an expression for tensor calculus that is all automatable so that the user never has to do it after the first time. And this really was a huge lift by Jeff Assel on the math and on Daniel A. Koene on the implementation of these things. And Michaela Bars pointed out to me that Jeff Assel no longer looks like that. So in fairness to Jeff, I put in a picture of me back when I looked like Jeff did at that time. So this is the work that Daniel and I have been working on actually just over the last 2 weeks, which is bringing in non-constant coefficients, stratification. This is an anelastic 3-density scale height convecting full sphere with internal heating with flows that actually cross the origin at the center there because the origin is captured in the thing. This is the entropy perturbation, the buoyancy variable in the system. So these seem to work pretty well overall. The spherical stuff is also all publicly available. It's hosted on GitHub right now under this kind of location. So those papers will be coming out for certain equation sets. There are published solutions that we're including with this. For more complicated ones, we're still learning what it takes to automate it. Turns out these non-constant coefficients have been extremely hard, and they've taken everyone on the team, Jeff Uichi, Keaton, Jeff Assel, Daniel, and myself working on it. And as soon as those are in a good spot, those will be available as well. So what can you do with a framework like this? What's the point? So the interesting thing in my mind, something that we stumbled across, we wanted to do low Mach number compressible convection at the outset. We thought we were going to be doing it in a fancier set of constrained equations. And we learned once we had the machinery in place that we could actually solve the equations in an entirely different way. So what we've learned that we can do, and which I'm going to talk to you about a little bit over the next couple of minutes, is we've learned efficiently how to solve effectively the full Navier-Stokes equations in the low Mach number limit. And what we've been able to do is to take the full compressible equations and move certain terms to the left-hand side that capture the fast sound wave interaction with the atmosphere and handle those implicitly, and so take steps that exceed their CFL criteria, while we then follow the nonlinear interactions explicitly, keeping the full thermodynamics and compressibility, not making some kind of global constraint on the system. And interestingly, this ends up working at both high and low Mach number, because at high Mach number, the nonlinear terms dominate the timescales, and so your CFL limit comes down to those sound speeds, and you kind of capture them correctly as far as we can tell. And then when you go to low Mach number, these that are setting your CFL timescales are now decoupled from these fast but linear modes on the left-hand side. So we've tested this in a few places. We've benchmarked it against the Athena code. Everyone loves the Athena code. It's nice, and it's frankly cheap to do. So the question is, like, is anelastic or something like that 10 times faster? We find that this kind of approach usually is about 50% more expensive than a competitive anelastic system, and that's because you're solving more equations. Then in the anelastic system, you can use stream functions and other things to reduce your number of equations. So here, the cost really is just going as a number of equations, not with the dynamics you're capturing. So what are the things we've done with this? So this is some work by Evan Anders, who's a grad student here at CU Boulder. Grad students get color pictures. So Evan has done some really beautiful work on fundamental heat transport and convection. We started working on this to try and see what we could answer in these systems and what of these systems is trustworthy. So Evan did a very nice set of studies that's published in PRF about a year ago, looking at low Mach number on the right and high Mach number on the right, low Mach number on the left for you, convection in stratifications of about 3 density scale heights, and then the left or the up and the down is what's the Rayleigh number and hence the Reynolds number of the flow. So the stuff at the bottom's turbulent and complicated. The stuff at the top is laminar and simple. And like, there's very little difference by eye between left and right, and the top and bottom, there's some difference, right? So there's some difference in turbulence parameter, but at least in these variables, there's very little difference in the structure, the convection, or other things as you go from a Mach number of 10 to the minus 2 to a Mach number approaching 1. If you have really sharp eyes, you'll occasionally see shock waves sweeping across the upper boundary here, where the convection is actually driving shocks. So that's about the only way I can actually tell which one's high Mach number and which one's low Mach number. And these are 2D runs because they're easy to show movies of. The interesting thing Evan did was doing a just boatload of these 2D runs, that's the dark colors, as well as some 3D runs, the pale colors underneath, and studying their heat transport of all of them. And they're an indistinguishable mess because they all fall in effectively the same scaling law, irrespective of the Mach number of the flow. So the purple stuff's Mach about 0.1 to 1, the red stuff's really pushing Mach number of 1, and the yellow boxes here are a Mach number of about 10 to the minus 4. And they all have extremely similar turbulent heat transport as measured by a Nusselt number and compared to their convective Rayleigh numbers. There's also extremely little difference, broadly speaking, between the 3D and the 2D. They have some slightly different power laws, and we actually understand where that's coming from. It has to do with a large-scale circulation that shows up in 2D and not in 3D. So flywheel modes, effectively. So that's fascinating. What's also fascinating is the scaling laws that come out of this in the box in the upper left are ones that look extremely familiar from the Rayleigh-Benard community. The stratified, fully compressible stuff under the right measurements scales like Rayleigh-Benard in terms of its heat transport, which is just telling us that it's boundary layer dominated. That's fascinating. Another very nice piece of work, again by a grad student at CU Boulder, Jet Bordwell, said, okay, so heat transport's interesting. Often we care about other transport. So this was transport of a passive reacting chemical tracer, basically, and Jet was able to find some very nice parametrized mixing models from full 3D simulations and was able to test them and verify that they work. They make similar predictions to other models in the literature, but they're vastly easier to calculate. So you can go and see Jet's extremely good paper on that to see some of their work. Okay, so back on the overshooting bit. So what about overshooting? So we got very interested in trying to study overshooting convection. So these are some different simulations with a stable region down below and turbulent convection above, here just in 2D because we wanted to get started and try and understand things. And we found some interesting things. The most interesting thing we found is that the amount of overshoot scales very strongly with the Mach number, and low Mach number convection that runs into a stable region stops extremely quickly. It radiates so many gravity waves as it drops into that stable layer that it robs itself of all of its energy and buoyancy, and it's like hitting a brick wall. So if this is true, then the tachocline in the sun would be an extraordinarily thin layer because it's having 10 to the minus 4 Mach number convection hit it, it's radiating extremely efficiently. There's a real problem with this work, which is that, and I'll try and make these slides available for later. This work's never been published. We've been sitting on it for 4 years. I showed some of those movies 2 years ago at GTP. And the thing that's held us up is a consistent question of like, well, are these things thermally equilibrated or not? Do we trust the amount of overshoot into that layer? And the answer is no, because the time constant down at the stable region there is just huge. And it's way more than we can simulate for. And so Evan and Jeff Oishi and I tried to find a way around this. And we found a way around this that I think may have some broader interest. And this will be my last couple minutes. And this is an idea that Evan came up with for accelerated evolution of convective simulations. The core idea was like, well, okay, so normally we start something and we run it forever and we try and burn into a solution so we can finally do some science. Could we get to that end stage faster? So the idea was you run a simulation for a while, you try and extract some turbulent statistics from that, like the amount of heat transport. You try and feed that into some sort of equilibration solution to find out what the structure should be that you're trying to get to, and you use that as the guess to continue the solution with. So this Evan did very successfully for an extremely simple problem of Rayleigh-Benard convection. I'm going to show you some results out of this. And you repeat this iteration until you finally are close enough you think to your final state. Now, let me show you for Rayleigh-Benard convection is lovely because we can actually run it for long enough to do both the straight up problem and also the accelerated problem. So at the top is Evan running a standard solution, as we call it, one where you start from noise at the beginning. That's at time 0. These are in free fall times, which are like the buoyancy timescale of the system. And you run it, and for 1,000 timescales, black line's the kinetic energy of the motions. The blue line is the temperature difference across the system. These are fixed flux at the bottom, fixed temperature at the top. And the way these systems evolve is that as the convection chews away with this insulating bottom, they drop that temperature difference down, 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 down. And it just slowly, 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 slowly drops on effectively a diffusive timescale. Evan runs it out to like 12,000 time units, which is a couple of diffusion times, and you hit a steady state answer. Okay, great. Now the box down here, Evan does the same solution, but after a couple of hundred free fall times, he stops, calculates the statistics, runs an equilibration solution, And suddenly the system jumps down to here, then he does it again a second time, then he does it again a third time, and then he captures the statistics. The green boxes are the same amount of time span. Here it's taken us about, I've cut it off the bottom, but it's taken us 800 time units to get somewhere interesting, of which about 400 have been science useful, 400 have been wasted getting to equilibration. Up above, it took us like 12,000 to get somewhere interesting for our same time span of interesting. Okay, so that's fine. Why does this work? I'm going to show you that it does work. One thing that's extremely interesting about these systems is that the thermal stratification takes a very long time to converge, but the turbulent statistics actually converge surprisingly quickly. So here's the time trace of the Nusselt number in this system, and the top box, again, is the standard that you run forever, and the bottom is the accelerated, where you cheat cleverly. And the top one, you can see the Nusselt number is fluctuating a whole bunch, and the character of the fluctuations changes in time, but the mean value of those fluctuations has saturated within a couple hundred overturn times. The thermal structure is still coming down very slowly, but when we look at the left panel and the right panel, essentially the same mean value of turbulent transport has been achieved well before the system has ever equilibrated itself. Down here is the same Nusselt number in the accelerated method, so you're messing with the system pretty hard, and then here on you're running to collect your data, and you can see that kind of broadly speaking, the accelerated system's behavior looks a lot like the standard system's behavior. Okay, that's still too hand-wavy for me to really trust. Turns out they're statistically similar as well. Evan studied over a whole bunch of parameter space, hey, how does like our amount of thermal difference change? How does the Nusselt number change? And then when you actually dive into the simulations, what do the PDFs of the thermal fluctuations and the PDFs of the nonlinear correlations look like? Have these things actually converged? The thermal fluctuations have a little bit of a discrepancy. That's because they were our convergence criteria and we were lazy, and our convergence criteria was let's not change by more than 1% between these iterations. Even with that weak of a convergence criteria, the nonlinear correlations and the convection, the PDFs of them are really close to each other. Okay, so this is some nice work by Evan. So what does this all mean? So I think we've learned a couple of things that are interesting. One, there's a really big outstanding question about deep convection in the sun. In some senses, until we know that, we don't know the rotational constraint of the sun, and we don't know where the dynamo of the sun lives. Is the sun rapidly rotating or slowly rotating? We don't really know. We've seen simulation indications of why this might be important. Two, well, we started out wanting to know what overshoot and the tachycline do in the dynamo. There's a lot of that we can't answer, especially without some sort of self-consistent tachycline, but there's some suggestion that these boundary layers in the deep interior of the sun might be pretty thin. That may change some of their role in the dynamo. Hard to say. What can we do going forward? An interesting kind of side discovery is that there may be ways to avoid spin-up costs. So we've done this for the absolute simplest case of thermal transport and Rayleigh-Benard convection. There are reasons why this might also work for things like the spin-up of a differential rotation and large-scale jets and the other things we spend a long time spinning up to. And especially when you go to spheres, and especially if you're trying to be at low Ekman number, like these things are just brutally hard to calculate. Like ask Nick Featherstone or ask John Arnaud and Rakesh about what it takes to spin up these very low Ekman number spheres. If we could short circuit some of those costs so we can get to the science faster, then that might be extremely beneficial for the kinds of questions we can ask. So that's what I've got. I'll take any questions that you have. Thank you.
So questions for Ben? We have time for a couple of them.
Just very good. I really like that. I have a question about your computational techniques and your pseudo-incompressible equation of state. So have you run that at low Mach number with the standard sod tube calculations for refraction waves and contact discontinuities and what happens?
So we've run that. We have run some shock experiments. And there are some really interesting issues in capturing shocks well in the spectral code. And Daniel has been working on that. We're going to have that actually probably in the instrument paper that we're in the middle of writing right now. So I don't have firm enough things. So in some senses, you can the shock part that's physically mediated is fine and is easy. The contact discontinuities are hard. So getting the contact discontinuities is very, very, very hard. It takes a lot of work. So
You said something about problems with variable coefficients. Are you talking about shear flows or something more complicated?
just non-constant coefficient, simple ones actually, things like density stratification with height. Those non-constant coefficient problems take a lot of care to compute correctly. The same would be true if you had some large-scale background shear flow, right? Like a Keplerian flow or something like that. But we have developed techniques for handling those in some kind of quasi-automated ways. So.
Step back.
Hey, Ben.
Ask away.
At one point you said that because the Mach number is low in the sun, it runs into a brick wall.
Yeah.
Here you said, A, we don't know what the speed of convection is in the sun.
Yeah.
Which one do you believe?
Well, even if the speed of convection is at the upper limits, it's still really low Mach number, right? So I think the question is, like, is it Mach number 10 to the minus 4 or 10 to the minus 6? If you're hitting the brick wall, it doesn't matter. But for the Rossby number constraint, the rotational constraint, that does matter, I think.
Yeah, I think there's a bit of an issue about whether you're hitting a brick wall because you're talking about average measures, and really what you need to know is the speed of the core of a downflowing plume and stuff like that.
True.
So, I mean,
and you might have
those are the things that penetrate.
You may have some real tails on these PDFs, and if it's highly rotationally constrained, that may actually let it penetrate more as well, right? Like there's some things that really could change this picture. Yeah.
Okay, I have a small question, Ben.
Ask her.
So in this simulation, are you changing this density by a lot from top to bottom?
In the left one or the right one?
The
answer is about the same.
Okay.
So in both of them, it's 3 density scale heights across the convection, both for the sphere and for the box, and it's like 1 density scale height of the stable region at the bottom. One thing that's different and interesting from the work Daniel showed earlier this week is that the waves that are driven here are driven to much higher amplitude than the convection that drives them. The color table's a little crazy, but the waves are like 10 times higher in amplitude. But that's because the only thing that's coming in and mediating them is diffusion, and the diffusion's lower down there. So. Right.
Well, let's take, there's one more.
Are there any deficiencies that you see because the acoustic modes are slowed down considerably when they hit?
Yeah. So we have no idea what this does to the acoustic modes that are driven. I have a grad student who's trying to understand that right now because he's doing a problem where he finally cares about the acoustic modes. But to really capture the acoustic modes, you really probably have to like run for a while till you're somewhere interesting, then suddenly vastly drop your time step, and now you can properly follow them. Right now, the acoustic modes that are being driven are probably spurious and probably are also too low in amplitude. That's right. They're basically the driving of them right now is just a like, hey, make sure that everything enforces the right kind of constraints of the regime you're in, but doesn't get their character correct, right? No.
Okay, one last question from Yuri.
You want to come and get plugged in?
Here's the last question.
Okay.
That's probably better.
Could you tell us when you foresee running the fully spherical Daedalus, how will you scale with processors? Can you run it on 100,000 or million cores?
Yeah, so we actually use the same scaling approach as Nick Featherstone's Rayleigh code, and that Nick really pioneered in the sort of early 2010s here and taught all of us about doing a proper 2D domain decomposition. So we've run the spherical Daedalus up to about 16,000 cores. The biggest limit there is that's about as much as Pleiades that you can grab at a given time. And we foresee it on large problems scaling out in the same kind of way. From our current studies, we're about a factor of 3 slower than Rayleigh. So Rayleigh, with its optimization and its Fortran, is a lot faster for the inelastic shell models. But we're kind of within the same broad order of magnitude and same kind of scaling. Those will actually be in Daniel's revisions to the instrument paper, so we'll have real numbers we can look at. So, and I'm sure all of those could be improved, and maybe we can help Rayleigh improve, and Rayleigh can certainly help us improve. So Nick and I are working a lot on that together. So,
All right, let's thank Ben again.
All right, the last talk of the session will be given by Lee Gunderson, discussing a model of solar equilibrium.
All right, is that a good distance?
Probably a bit higher up. Yeah, a bit higher. That should do it.
How about that?
Yeah.
Okay. All right. Good afternoon, everyone. So today I'm going to talk about an equation that you might have heard of before, applied to something that you've definitely seen before, but the combination of which I hope you find novel and interesting. So first I'm going to talk a little bit about how we know what we know about the sun, and then I'm going to talk about how we think an equilibrium description might be useful. Then I'm going to outline the Grad-Shafranov equation, which describes these equilibrium states. And then I'll talk a bit about this formalism applied to the hydrodynamic limit of this formalism applied to the outer layers of the sun, which will appear in AppJ in this month or next month. And then I'll give a little bit about current work that includes a magnetic field for the tachocline radiative interior. So our relationship with the sun is as old as humanity itself, but far from being an immaculate Aristotelian sphere of the heavens, this rather ordinary star is close enough to us to reveal its imperfections. And it's through these imperfections that we've grown to learn about this entity that, upon which we so depend. So sunspots can be seen even with the naked eye, and they were first noticed, well, they've been noticed since antiquity, but the earliest record is from the Chinese Book of Changes around 800 before Common Era. And then about 2,000 years later, we have the earliest known drawing of them. But it wasn't until the 17th century that these dark spots were identified as surface features, and that their systematic motion implied that the sun rotated on its axis. 200 or so years of piecemeal observations later, Schwab noticed that they came in 11-year cycles, the first implication of the solar magnetic cycle. And then a bit later, Carrington noticed that the ones near the equator rotated faster than those near the poles, which was the first implication of solar differential rotation. So that's not so bad with naked eye observations assisted by optics, but at the risk of sounding temporally solipsistic, with modern technology comes modern understanding. And one of those modern techniques, which we've heard of about a lot this week, is that of helioseismology. So much in the same way that we can learn about the terrestrial interior by looking at how earthquakes bounce off the inside of the Earth, we can look at sunquakes and their dynamics to infer how what the interior of the sun looks like. And fortunately for us, the sun is quaking all the time. Supersonic convection at the surface drives sound waves, which set up global standing modes. And by measuring the surface velocity, we can resolve hundreds of thousands of these frequencies. And each of these frequencies corresponds to an eigenfunction that samples a different spatial region of the sun. And so now we have a monster of an inverse problem, one whose goal it is to take in these frequencies and generate an internal profile of the sun that resonates with the spectrum. So I like to classify helioseismology into three different categories, arranged in decreasing assumption of symmetry, which is unsurprisingly also their chronological order. So first is what I like to call spherical helioseismology, as it assumes that the sun is a spherically symmetric ball of gas. So if you think about solving the wave equation in spherical coordinates, but with a radially varying speed of sound, then the problem becomes to come up with a profile for this radial profile of the speed of sound, such that the frequencies that such that the eigenvalues that you get are equal to those frequencies that you observe. And so if you do this, you can, if you get the speed of sound as a function of radius, along with the gravitational law, hydrostatic balance, and some knowledge of the equation of state, you can back out the radial density, pressure, and entropy profile. And it's the abrupt flattening of this entropy profile at around 70% of the solar radius that was the first time that we really pinpointed the base of the convection zone. So spherically symmetric is a pretty good lowest order approximation, but the sun does indeed have a preferred direction, namely its rotation axis. And so this leads to the second category, which I call cylindrical helioseismology. So the sun's only weakly rotating, it's mostly gravitationally dominated, and so these eigenfunctions are going to look pretty similar to those in the spherically symmetric case. And if you recall, the spherical harmonics have a degeneracy, namely, either sign for the azimuthal wave number m gives you the same frequency. However, if you introduce rotation, the toroidal flow can Doppler shift these frequencies, upshifting the prograde modes and downshifting the retrograde modes. And by analyzing this frequency splitting, it's possible to back out the interior rotation profile of the sun, now as a function of radius and latitude due to the relaxed symmetry constraints. So we only have one symmetry left, and there's still space on the bottom of the slide. So we have nothing left to do but discard symmetry altogether for the third one, and that's known as local helioseismology, because it doesn't rely on any global modes of oscillation. Instead, it looks at correlations between activity on the surface. So you look at the activity at one point and then measure the correlation with some other point, some distance away and some time later. So a perturbation at point A excites sound waves in all directions. And since the speed of sound increases with depth in the sun, these sound waves will refract and bend back and appear at the surface some distance away and some time later. And so, again, in the spherically symmetric case, you would expect that the transit time from point A to point B would be the same from point B to point A. But if you introduce flows, in particular one that's going from point A to point B, then the time that it takes for the wave packet to travel in that direction is going to be slightly shorter than expected, and likewise slightly longer going back. And since we know the sound speed profile, we can figure out the trajectories of these rays. And by looking at the difference in these transit times, we can get an idea of the integrated velocity along those trajectories. And by combining together a bunch of different directions and different depths of penetration, it's possible to back out the poloidal flow, again, as a function of radius and latitude. I should note that in cylindrical helioseismology, it's not sensitive to poloidal flows. And in local helioseismology, it's mostly sensitive to the horizontal flows and not so much to the vertical. So arguably, one of the most beautiful pictures to come out of this general endeavor is from cylindrical helioseismology, namely the internal rotation profile of the sun, which I'm sure you've seen before. So it can be separated into two broad regions. You have the differentially rotating outer part and the inner part, which is not. So this outer part, as I'm sure you're aware, is known as the convection zone, and it's characterized by a faster rotating equator and slower rotating poles. And the isorotation contours are tipped reasonably radially, especially at mid-latitudes. This interior region is known as the radiative interior because its primary mode of heat transport is radiative diffusion. It's stably stratified and characterized by a markedly uniform rotation. So this is like a broad strokes look at the sun, but interesting things happen at the interface as well, and so it behooves us to give names to these boundary regions. So at the boundary between the convection zone and, well, space, you have the near-surface shear layer, which is in about the outer 5% of the sun, and it's characterized by a slowing of rotation as you approach the surface. It's actually interesting. This was implicated before even spherical helioseismology. It was noticed that sunspots rotated systematically faster than the Doppler measurements of the surrounding photosphere. And it was posited that these magnetic features were anchored at some more faster rotating lower layer. And indeed, this picture confirms that. So while this outer layer was somewhat anticipated, the inner boundary between the convection zone and radiative interior, known as the tachocline, came as a relative surprise. While we knew that this is where that this was the region where convection onsets, it was not really anticipated that you'd have such a sharp transition from this differential rotation to uniform rotation in the interior. So, as we've heard a couple times this week, the tachocline remains enigmatic, and so I figured that another slide on it was warranted. So it's a region of strong shear at the base of the convection zone, and as was just mentioned, it's quite likely unresolved. This might not necessarily do it justice here. And this region is important for a lot of solar models, like Babcock-Leeton models of the solar cycle. This is where the omega effect that stretches poloidal field into toroidal field often occurs. It's important for elemental mixing. The precise nature of the poloidal flows in this region determine a lot about how the different elements move around the interior of the sun. And it's also important for solar spin down. Actually, before we could see the internal rotation profile, there were some people who thought that maybe the interior was rotating at 10 times the speed of the surface because that's how fast the sun was rotating when it was formed. And then as it sheds its angular momentum, maybe this didn't get communicated to the interior. So it's actually kind of surprising that the value that the interior rotates at is pretty much the average of the differential rotation. So despite its importance, a lot of models sort of enforce its existence in an ad hoc sort of way, either by just positing a rotation profile, as is done in a lot of Babcock-Leeton models, or by some sort of external forcing term to keep it there, or some specific boundary conditions or radial profiles of diffusivity. Right. So, given all these questions, it seems like it would be a good idea to take a step back and ask, okay, what aspects are actually important for describing the features of the sun? And as the title suggests, I'm proposing an equilibrium model. So the sun is a very complex and complicated object. So somebody might rightly ask, what hope does an equilibrium model have to describe such a dynamic system? Well, to this man made of straw, my answer would be that equilibrium models can provide remarkable insight, even when applied to notably non-stationary systems. And there's a nice parallel example. Take, for example, the canonically turbulent solar wind. So Parker, with just a laminar 1D hydrodynamic model, was able to correctly infer that the solar system is permeated by a supersonic outflow. And he actually got the velocities pretty close. Weber and Davis, a little bit later, extended this to the MHD case, but still in a 1D model, and pointed out the importance of the Alfvén radius. So the Alfvén radius, inside the Alfvén radius, the magnetic field dominates over inertial forces, And so the field is effectively radial, and the fluid effectively co-rotates with the star. Outside of this radius, the fluid becomes free streaming, and then you get the well-known Parker spiral. And it's this Alfvén radius that sort of serves as an effective lever arm for how the sun sheds its angular momentum. Extending this further, Sakurai considered a 2D cylindrically symmetric MHD model of the solar wind, and this gave an idea as to sort of the spatial structure of these outflows, whether they're collimated or along axis or along the equator. And actually, the equations that he solved are known as the Grad-Jafranov equation, and that's the equation that I'm proposing to use for the sun. It's got quite a rich pedigree of applications. I first learned about it in the context of in the magnetostatic context for magnetic confinement fusion devices. But it also has a wide variety of astrophysical applications. So its relativistic generalization has been applied to accretion disks. Superconductivity has been included for neutron stars, and even structures within the solar wind. So if you imagine you have like a coherent tubular type structure flying through the solar wind, and you have a spacecraft that just gets a single line of data as it flies through, well, you can look at that in the 2D plane, and you have like one line of data in a 2D plane, and then you can use the Grad-Jafranov equation to sort of extrapolate away from this data that you have to make a plausible picture of what that 2D structure might look like. So yeah, given its success in producing plausible equilibrium models from incomplete observational data, we propose application to another compact astrophysical object, namely the sun. Okay, so now I'm going to just briefly outline the equations. It won't hurt. So we start with ideal MHD with a gravitational potential and assume adiabatic flows. And with the assumption of axisymmetry, you know that you can decompose a divergenceless magnetic field into its toroidal and poloidal components, with the poloidal component being described by a scalar flux function. And likewise, with the mass flux, you can do the same. And the equation that relates the two, Faraday's law, under the assumption of axisymmetry, it actually has a surprising consequence, namely that these two surfaces coincide. The poloidal field and the poloidal flow are parallel. So when you talk about flux surfaces or stream surfaces, in this context, they're the same thing. One other interesting thing that comes through the algebra is that there's some physical quantities that end up being constant along these surfaces. So for example, entropy here, V dot grad of entropy is 0, so you know that entropy is constant along in the direction of flow, and so you know that entropy is a constant along these flux stream surfaces. And hidden in here are 5 others, free functions. So these are scalar functions of, okay, let me explain. So this chi here is a label of these flux stream surfaces, just a sort of an arbitrary scalar label. And then along with the entropy, which is a function of only this label, you also have 5 others related to the density and toroidal and poloidal field and flow. Loosely, they're not exactly, but they're strange combinations, not worth writing. Right. So with these reductions, you can reduce the 3D momentum equation into a nonlinear 2D PDE for this flux label, chi. And that looks like this. And the main thing to notice about this is that it can be of mixed type. It can be both elliptic and hyperbolic within the same domain. And the boundary between these regions is not necessarily known a priori. This equation is augmented with something analogous to the Bernoulli equation. And so this is an algebraic expression for the density rho. And you might think that that makes it easier. It's not a PDE, it's just I'll just use a root finder. But in general, it has up to 4 roots, and picking the correct one algorithmically is often a headache. So one more thing to notice, this quantity here. So these are constant along stream surfaces. And so if a stream surface wants to cross a surface of a particular critical density as determined by these quantities here, then the equation becomes singular. You have it showing up here in the differential operator, and it shows up in the denominator down here. Just one thing to point out is that, so if a flux surface wants to cross that particular critical density, then this quantity must also go to 0. And so, in fact, the cylindrical radius lambda must be some other particular value. So in essence, this surface of critical density sort of tethers these surfaces to them at a particular point. I'll get back to that. Right. So now I'm going to talk about some results for the hydrodynamic limit applied to the outer layers. So what sort of questions might an equilibrium code be able to answer about this? Well, one big question is, why are the contours tilted the way that they are? The Taylor-Proudman theorem says that they should rotate on cylinders. A barotropic fluid should rotate on cylinders. And so if it's not rotating on cylinders, you need a source of azimuthal vorticity. And the commonly posited source is that of misaligned pressure and density contours. And in a gravitationally dominated case, this is summarized by the thermal wind equation shown here. So this is the differential rotation and the latitudinal entropy gradient. And if you look at how much of a latitudinal entropy gradient you need, you actually only need the poles to be about 10 degrees Kelvin warmer than the equator. Yeah, poles warmer than the equator. And this is below observational, below what we can observe conveniently. Right. So this is one equation with 2 unknowns. And so Bulbus of accretion disk fame thought that he could make a nice simple model by assuming a closure to close this system. So he assumed that entropy was a function of rotation only, and that gives a nice algebraic equation by which one can prescribe rotation and entropy on the surface and uniquely extrapolate it to the interior. And he got something that looks like this, which gets reasonable agreement in the bulk of the convection zone, but does notably deviate in both the near surface shear layer and tackle climb. So this expression here looks surprisingly like those those free functions. And so in fact, we took the hydrodynamic limit of the Grad-Shafaranoff equation and included the other appropriate assumptions and found that it reduces to thermal wind balance as expected. But you're left with something else. In the hydrodynamic limit, angular momentum turns out to be one of these free functions that's constant along these surfaces. And since entropy is as well, that implies that entropy should align with angular momentum instead. And so if you use this alternative to Bulbus's ansatz, then you get something that actually agrees almost as well in the same regions of validity. But we can actually go one step further. Still within the hydrodynamic limit, we can include a poloidal flow. And when we include a solar relevant poloidal flow, we actually get something that's reminiscent of the near surface shear layer. So what you're looking at here is data on, this is helioseismology on top. This is rotation as a function of radius for several choices of latitude. And this is the same for our Grad-Shafaranoff model. And so you can see the similar agreement in the bulk of the convection zone, and then this qualitative reduction in rotation at the surface, albeit a bit smaller. So again, there's no tachocline in either ours or Balbus's model, and so this motivates the inclusion of magnetic fields. Definitely not the first person to suggest this. So we kind of want to make something that looks a bit like a GO and McIntyre model. So as a first step, this is including a toroidal field. So this has a very weak poloidal field and a toroidal field that's consistent with upper bounds at the base of the convection zone. And so you can see that it can change the rotation profile in the deeper interior, something that looks, even a bit more solar-like here. And the only difference between these plots on the left and the right is the sign of the toroidal field. It's kind of interesting that even though the poloidal field is vanishingly weak, when you force with all of the conservation laws and everything, the allowed equilibrium states look notably different. Okay, so the magnetized interior. So I mentioned before that that term that could go to 0. The relevant parameter to keep your eyes on is something called the poloidal alphanic Mach number. That's what happens when you take the poloidal field and flow and make an alphanic Mach number out of it. So if you look at the determinant of the PDE, which is positive when it's elliptic and negative when it's hyperbolic, you'll notice that it changes sign at 3 critical values. And so when the poloidal flow is weak, very weak, you're in an elliptic regime, and then you have a brief region of hyperbolicity between 2 of these values, and then you're back to elliptic, and then when you're supersonic, you're hyperbolic again. So it's actually this little region of hyperbolicity that's rather interesting. For tokamaks, it can cause instability, which would seem bad, but these transitions can also make shocks, where you have large density gradients and strong shear, which can serve to provide internal transport barriers, which is good. And actually, there's a series of papers by Goodblood that looks at exactly this hyperbolic region within the context of accretion disks and posits that it might be a source of turbulence not yet looked at. But in the sun, we're in a different regime. It's gravitationally dominated, so the pressure dominates over the magnetic field, and the poloidal field is weaker compared to the toroidal field. So in this limit, the thing to notice here is that those 2 critical values that were around that relevant region of hyperbolicity appear in a very narrow band, really close to poloidal alphanic Mach number of 1. So where does this, where would a poloidal, what are the values of the poloidal alphanic Mach number in the sun? So if you use the poloidal field and flow at the surface and extrapolate downward, at the surface it's about 200, and it decreases inversely proportional to density. And so if you look at where that should happen, it happens suggestively close to the base of the convection zone, the location of the tachocline. And so this is our hypothesis that this is not a coincidence. So I'm almost out of time, so I'll just leave the take-home message up there.
So Steve Balbus in his models had this concept of residual entropy.
Mm-hmm.
So you're saying, forget about that, just use entropy?
So I felt that would take us on a unnecessary digression. So we assumed a similar form to his residual entropy, assuming that you have a radial entropy gradient that's sort of in dynamic equilibrium with the convection, and then that what he calls the residual entropy would be what we put into our equation as the entropy in those equations. So,
what's
sorry.
the difference then? So what is the difference?
The difference is the alignment of that residual entropy. He still aligned it with the rotation as compared to the angular momentum. It should be noted that he did consider an alignment with angular momentum in one of his first papers, but discarded it because it didn't look like helioseismic observations, but you can make it look pretty similar, in fact.
Okay, thank you.
Any additional questions?
So under what conditions do you get that alignment? They're the conditions of your equation set, basically. But what are those? What's the physical constraint, sort of simply said?
Right. So if you assume adiabatic flows, then in completely ideal MHD with no dissipation or anything, then those flows should conserve in the hydro limit should conserve angular momentum, and so probably the weakest. The weakest assumption is that of adiabatic flows. I mean, in the convection zone, the correlations between velocity and entropy are the primary mode of heat transport as compared to mean flow advection. And so to the extent that you can sort of brush that under the rug, that's when you get the alignment.
Did you say that the near-surface shear layer is caused by meridional circulation? Is that how you produced it in your one of your last models?
Right, right.
Yeah. Okay, thank you. And in your introduction, you made an interesting point that the original explanation for the rapid movement of young sunspots was that they are anchored a little bit deeper, but in both cases, the sunspots would be anchored within the near-surface shear layer, right? According to your introductory description. Young sunspots are faster.
Right.
And that's where...
In general, the larger sunspots rotate faster because they're anchored deeper, no?
Yes, exactly. And then they slow down.
Right.
So you would think they are at a shallower depth.
Right. As they evolve and get smaller,
and that means we should have a negative gradient in the angular velocity with radius. And that we have only in the near-surface shear layer.
Right.
So the sunspots would then be anchored in the near-surface shear layer, not at the bottom of the convection zone. Or the
sure. Yeah.
All right, any final questions? All right, let's thank the speaker again and all the speakers in this session.
All right, it's that time in the day. Beer 30. Actually, it's beer 39. Thank you all for coming this last few days and for participating in what's been a great discussion. I'm sorry that I didn't get to participate in more of it. Particularly want to thank the other members of the SOC and Cheryl Shapiro, who's probably listening. Kim, thanks for your help in setting everything up. That's the majority of HAO's team that participates. Calvin, if he's up there, he can make the lights blink. Thanks, Calvin. And the multimedia crew here. All your talks have been recorded. You signed the waiver, right? And they will appear on our YouTube channel and linked to the agenda, but in blocks. We probably won't separate them out. So if you want to use that material, feel free to do so. But I can't think of anything else but to say bon voyage, safe travels home. For those of you who are hanging around NCAR to work with collaborators, then I hope you enjoy the remainder of your stay. But thanks again to you all. Without you guys, things like this can't be success. And I think this has been a good success this week. So thank you. Big cheers from me. And farewell till the next time.